Well, let us first start with neutron stars and pulsars, which are a subset thereof. This is a picture of the Crab Nebula, which doesn't look like the picture of Crab Nebula you know and love because it's taken in X-rays. And the gas that's emitting in X-rays, or rather electrons, has a different distribution. First, about the origin of neutron stars. They always come from supernova explosions. And as you probably recall, if the core of the collapsing star is more than the Chandrasekhar mass, then even the degeneracy pressure of electrons cannot sustain the gravity of the core and it has to collapse. But as it does that, temperature is, of course, in many billions of degrees. Gamma rays are overabundant. They dissociate any nuclei, helium or anything else. So essentially what you have is a lot of protons and electrons. Now that is such a density that actually electrons and protons combine, producing neutrons and emitting neutrinos. And what you end up with then is a whole lot of neutrons, which are also fermions, following Pauli's exclusion principles. So now neutrons do what electrons did for white dwarfs. They create this new quantum mechanical pressure that sustains against gravity and stabilizes what's now a neutron star. And those neutrinos that fly away, well, essentially they're cooling off this collapsing core, take away energy. They actually take most of the energy in the supernova. The stuff that you actually see is maybe 1% of the total energy. Most of it is in neutrinos that are generated in this process. So then, essentially what you have is almost like a gigantic atomic nucleus composed of neutrons and probably some other exotica. And the density is the density of atomic nucleus because it's an incompressible degenerate fluid. And so it doesn't matter whether it's a handful of nucleons or a whole lot of them. And when you divide mass of, say, 1.4 solar masses by the density, you find out that the radius of such a structure is about 10 kilometers. So you get nearly 1.5 masses of solar masses worth of stuff compressed into the size of, say, less than the inner Los Angeles. Well, no wonder this is pretty dense, and there will be very strong gravity. We think we know what the actual structure of neutron stars is. These are from theoretical models, but they're confronted with observations of pulsars all the time. And interestingly enough, most of this neutron fluid, if you will, is superconducting or superfluid. Usually think of things that are really cold, like helium, liquid helium that can go into superfluid state. But for nuclear matter, it actually can be in millions of degrees. And because of that, the interior of neutron stars can be an excellent conductor, and that's why they can retain the magnetic field so well. Now, it's possible, I would say it's probably likely, that in the central parts of a neutron star, you have more exotic stuff. People even talk about quarkonium liquid, but that's a whole other story. And the very surface of it may be composed of ordinary matter. Largely, those will be the iron group elements. Remember, those were kind of the final product of nucleosynthesis. So whatever was retained within a collapsed core will tend to form this iron crust that encloses this gigantic drop of neutron superfluid. Of course, such things we can never do in the lab. So this is why neutron stars provide insight into extreme states of matter that we just cannot do any other way. Well, how did this all come about? Neutron itself was discovered in laboratory in 1932, and already 2 years later, two of Pasadena astrophysicists, Walter Bade and Fritz Zwicky, who were studying supernovae, which around that time they figured out are not the ordinary novae, but a completely different phenomenon. They speculated they come from collapse of a very massive star, and that core of a star could become a neutron star. It was a prediction way ahead of its time. Now, that was pretty much untestable for a while. And then with the birth of radio astronomy, a graduate student by name Jocelyn Bell was doing her thesis in Cambridge, and she used a radio telescope that looks like this. It's a whole bunch of wires and sticks, but those are actually dipoles. And for some other reason, they're probing celestial radio emission millisecond timescales, looking for scintillation. And so she discovered there was a periodic signal coming from some directions, some tens of or hundreds of milliseconds. And it was rotating like a sky on sidereal rate. So this was completely unexpected because it was rotating on sidereal rate. Clearly had to be somewhere out there in the universe. There was nothing ever predicted like this, and all kinds of models of advanced, including that those could be signals of extraterrestrial civilizations. But then her advisor, Anthony Hewish, figured it out, that these are actually rotating neutron stars. The key to this was that the pulses themselves are very narrow, millisecond or less. And the flight time of 1 millisecond covers only a couple hundred kilometers, so the region from which those pulses are coming couldn't be more than a few hundred kilometers. Now, white dwarfs are more like several thousand kilometers in radius, and they cannot be compressed any further. That's why they are the white dwarfs. And so this could only be something else, and the only other thing that was anywhere in the literature would be neutron stars. So this is what pulsars really are. In addition to inheriting all this mass and achieving high density, they inherit two other things from the progenitor star. The angular momentum, which, as you recall, cannot be radiated away, so it has to be retained. And because it collapsed by a huge factor, then they'll start spinning really, really fast. And also the magnetic field that was trapped in the plasma will be pulled down in that collapse, highly concentrated, and the prevailing dipole magnetic field can serve as a particle accelerator. Now, in general, the magnetic poles and rotational poles did not coincide. This is the case on planet Earth. Our magnetic pole is not a north geographic pole, but it's a little off. And so that means that this magnetic dipole will keep rotating. And if it accelerates particles along the magnetic lines of force due to Lorentz force, then the beam of those particles and any synchrotron radiation they emit will be sweeping around the sky in a cone. And so if we happen to be in the beam, we're going to see pulses. So it's just like a lighthouse, although in radio waves. But that also means there are many, many more pulsars out there than we see, because we only see those that happen to be pointing at us. But that all fits with our estimated rates of supernovae and what have you. So that's the basic model of how pulsars work. And they're all discovered in radio. The new preferred model of discovery is through gamma rays with the Fermi mission. And there are few that are also seen as visible light pulsars. Crab pulsar was the first one of them. There are two little stars in the middle of Crab, and the western one is the pulsar itself. And so it pulses. What's shown here on the right is a sequence of video frames, and you can just see it come and go. And then it does the same thing in X-rays, and this was measurements with Chandra satellite. Doesn't have the same angular resolution, but you can see the point source come and go at the exact right pace. So Crab is probably the best studied pulsar. It emits at all wavelengths. It's bright, relatively speaking. It's one of the youngest we know. And it served as a milestone for many of the other studies. So this is what happens when you take the light curve and fold it by a period. And the period is indicated there in the upper right corner. You can see from the number of significant digits that these things are measured with an exquisite precision. It's not that their calculator has 10 decimal places, so they just wrote them all down. It actually is that precise. And because of that, those are really precise clocks. So now that you know period, you can fold the data again and again and again, and you get a beautiful curve like that. And you can see there is a big pulse and there is a smaller pulse between, and that's since the beam goes around both ways. Okay, so the pulsar timing then became a very useful tool because pulsars have humongous moment of inertia. You guys can compute those on Friday, say. Then they'll be very stable in their spin period. And they're as good or better than the atomic clocks we have on planet Earth. So actually, at one point, there was power interruption in Arecibo, and they tuned their atomic clock according to the pulsars they were monitoring. Well, all right, so they radiate. That radiation has to come out of somewhere, and the only or the main source of energy that's available is the rotational kinetic energy of the neutron star. So that's 1/2 moment of inertia times the angular frequency squared, right? And that will be inversely proportional to the square of the period. Now, luminosity is the change of energy per unit time. Because energy is going down, it's negative, right? So minus will have to compensate with a minus from derivative. This is a simple derivation, and luminosity will be directly proportional to the period derivative in time, which you can measure using pulsar timing. And shown here is somewhat schematic representation how people actually observe periods of pulsars slowly growing. Now, occasionally there is a glitch. It drops down a bit. And since the only way it can do this is by changing its moment of inertia, essentially pulsar rearranges itself a little bit. It's the star quake. So that it goes into slightly lower energy state of rotational motion, and then continues doing the same thing again. So these are probably star quakes that are with amplitudes of some millimeters. The biggest mountains on these neutron stars are probably millimeters high. But nevertheless, they can be observed very easily. You may also remember that this enabled people to discover planets around pulsars because you have very precise clock going around, and you can measure Doppler shift of the arrival of the pulses, just like you do with radial velocity, and this is how the first extrasolar planets were found. But the really cool thing happened when the first binary pulsar was found. Since a lot of stars are in binaries, sometimes you're going to get massive star binary, both of them will explode, and both of them will leave a neutron star. And those two neutron stars will orbit around common center of mass. So the first one of those was found by Joe Taylor and Russell Halsey. Russell was a summer undergraduate student. So who knows, one of you doing surf today might get Nobel Prize sometime in the future. So they found this binary pulsar with period, I think, 7-something hours. And they can time it very precisely. Now, what happens when you have such massive binary at such close separation, relativistic effects start coming in play. One of them is that two masses rotating will start creating gravitational waves. And those gravitational waves have to come at the expense of something. They come at the expense of the orbital kinetic energy, just like pulsar emission from internal rotation of the pulsar. This is from the rotation of the binary. And when they compare that with predictions of theory of relativity, they saw this. You never see such fantastic fit in science. This is amazing. Because of this, this was essentially first detection of gravitational waves. They could have closed the LIGO shop right then, but they didn't. These guys got Nobel Prize for the discovery. And something else interesting can happen with pulsars. So if they're in these binaries, they can be accreting, well, just like with white dwarf binaries, you can have X-ray binary that contains a pulsar, and those are seen and called X-ray bursters. But in some cases, or maybe most cases, what happens is this material is being accreted onto the neutron star, and it comes with some finite angular momentum. So neutron star soaks up not just the mass, but also the angular momentum and spins up. And turns out you can do this in some circumstances to speed them up to about millisecond period, which is phenomenal. So that then became a whole new industry of precise pulsar timing, because it's even more precise clock with shorter period.